Hey, good afternoon, everybody. So I, of course, want to thank the organizers for having me here and speak about physics for once. I'm also, of course, incredibly happy to wish Giorgio a good 70th birthday and add my little pinch of salt on the story. For me, it's 35 years of awe. For those of you who are not completely sure of the meaning of this word, I checked in the dictionary.com yesterday evening. It means an overwhelming feeling of admiration, which I think is very appropriate. It also has a tinge of fear. And you know, you can believe me when you're a young PhD student, as I was 35 years ago, and you hear first about Giorgio's theory of spin glasses. It was a talk at École Normale given by Gérard Toulouse. You feel, wow, am I even going to be able to do anything in this in the field of physics and diagonalize 0 by 0 matrices? It's going to be hard. Anyway, so I want to, I could go on about stories, how Giorgio influenced me until now. For example, yes, I wanted to mention the 1986 Les Ouches session, where Giorgio gave a series of lectures that was also very influential for me because it convinced me that these older systems were really great. And it was a course on the cavity method. I think Giorgio and Miguel and Mark just understood the cavity method, and you could feel that Giorgio was extremely excited about this, and he could convey his excitement, and it was so clear and interesting. Anyway, so what I want to tell you about is actually a long story that started 15 years ago about this idea of trying to use nonlinear susceptibilities to understand what's going on in glasses. And we've interacted with many people, in particular with Giulio, who gave a talk this morning, and François Ladieu, who's an experimentalist in Saclay. And so what I'm going to present is of course, the result of the efforts of a lot of people here. Okay, so you're going to hear again many things that you've heard today by Victor, by Patrick, by Mathieu, but I'll try to give my own flavor to this. So I'll want to go back to basics in a sense and talk to you about rigidity and long-range order, and cite another awesome hero of mine, Phil Anderson, who says we are so accustomed to the rigidity property that we don't accept its almost miraculous nature, that it is an emergent property not contained in the simple laws of physics, although it's a consequence of them. And what he means by that is rigidity, it means the relevance of boundary condition. So this is a little picture taken from a beautiful paper by Hajime. You change the boundary condition of a system, of a very large system, and you still expect something to happen if there is rigidity. You expect the energy to change, and this would not be possible, of course, if there was no kind of long-range order that allows a particle deep in the bulk to feel what's going on at the boundaries, and some sort of ergodicity breaking. And in the example of the shear modulus of solids, you can actually prove that the shear modulus can only be non-zero if the dynamics is not able to probe the whole phase space. And a more formal way to see that is this exact thermodynamic formula of the shear modulus that's given by a simple affine contribution, which is just seeing how much energy you have to pay to affinely deform the system. But there's also a thermal contribution, which comes from fluctuations with a negative sign. And in an ergodic liquid, you can show that sigma squared exactly compensates P, so that G is 0. And for those of you who want to understand that better, again, Hajime's paper, long paper, but very beautiful, is interesting. Okay, so long-range order, we know many examples of that, so let me go back to the simplest example of all, which is a continuous phase transition, say, of the Ising type. And what we know in this case is that the spin-spin correlation function decays exponentially, but with a length scale that is going to diverge at the critical point, and a power law correction. And as you reach the temperature at which the system orders, Xi diverges, and the time scale, the relaxation time of the system also diverges with the power of this Xi. And an interesting physical picture of what's going on that you can make very precise, and Antonio Cornelio, who's in the room, contributed to that, is to think of the system organized as fractal clusters of kind of rigid spins. These fractal clusters have a dimension df and its size Xi, and when you put a magnetic field to the system, these fractal clusters rigidly respond to the field. And so what it means that if you want to compute the magnetization, for example, well, you just have to count the number of blobs of size Xi, L over Xi to the D, the contribution of each blob, Xi to the df, and then a function that compares the magnetic energy of Xi to the df times mu dipoles in a field of strength h to the thermal fluctuation kT. And if you assume that f, which should be an odd function, is just linear for small x, then this formula leads to a diverging susceptibility that takes at non-zero frequency the following scaling form: Xi to the 2df minus d times a scaling function of the frequency times the relaxation time that I talked about. So in particular, you see that the way this static susceptibility diverges is giving you indication on the size of these blobs and the fractal dimension of these blobs. Of course, you could have gotten the same result by using FDT and integrating the correlation function. So, as been again mentioned by the previous speakers, the glass conundrum is that the glasses below the experimental temperature Tg are, for all intents and purposes, rigid on experimental timescales. That's what the basic phenomenology of glasses is. That so it means that ergodicity is effectively broken on the relaxation timescale of glasses. And I think this is simple, but this is basically the problem that we have to address. And of course, the conundrum comes from the fact that compared to systems that order, molecular configuration in a glass are indistinguishable from those of the liquid. And so there's an amorphous solid which is rigid, but there's no order. So how to explain this? There are two kind of extreme opposite viewpoints, and of course a lot of intermediate viewpoints possible. That also relates to Patrick's quote of David Weitz. There's a point of view that nothing much happens in the system. There's no thermodynamics is irrelevant. There's a local slowing down of the system. Say the barriers locally become large, and the system is just slowed down because even the elementary events are slow. And then there's maybe a more exciting, or I don't know, at least for me, a point of view, which is that there is a true underlying thermodynamic transition that drives what's going on. And this thermodynamic transition is towards a strange phase that is still amorphous but has long-range order. So, amorphous long-range order, that sounds like an oxymoron with words that seem to contradict each other, but I'll try to give you insights into that. And of course, this field is very old, and there's been arguments about the phase transition and hints of this phase transition since the late 50s. For example, and these are a little bit tarte à la crème pictures to show, you've seen that one already before. The relaxation time, at least in fragile liquids, increases extremely quickly when you decrease temperature for an order of magnitude. Remember that for these very fragile liquids, you can increase tau by 10 to the 10 when temperature only decreases by 10%. So it's a pretty spectacular phenomenon. The other thing is this well-known correlation between the relaxation time and the excess entropy of the supercooled liquid over the crystal. And for a variety of different systems, there seems to be a large correlation between what the excess entropy is doing and the relaxation time. And this is also being discussed just by the previous speaker. So, if we believe that some kind of amorphous long-range order is setting in as the system becomes slower, we need to try to define and measure a correlation length that would characterize this long-range orders, incipient long-range order. So again, citing Anderson, he says, some but not all transitions to rigid glass-like states may entail a hidden microscopic order parameter, which is not a microscopic variable in any usual sense, and describes the rigidity of the system. So, a very well-known, at least here, example, but I would like again to come back to basics here, is given by spin glasses. Spin glasses really provide a concrete example of what amorphous long-range order may mean. And as you well know, these are systems with random interactions that lead to a random but frozen configuration below the spin glass temperature. And these configurations are not really different from what they look like at higher temperature, except that they're frozen. And in this case, the spin-spin correlation function, well, it oscillates. It has no definite sign. So instead of looking at just the spin-spin correlation, you have to square it. Victor this morning explained that in a little slightly different context. And then if you average the square of this correlation function when x and y are at a certain distance r, then you find again that this, as you approach the spin glass transition, is of an exponential form divided by some correlation length L, I called psi before. Here for the spin glass, I call it L. And again, some prefactor, algebraic prefactor, parallel prefactor. And again, the physical picture can be framed in terms of fractal clusters. Now these fractal clusters are of randomly frozen spins in random directions with some fractal dimension df and size L. And now, because these spins are frozen in random directions, the resulting magnetic moment is not mu L to the df as I told you before, but rather mu L to the square root of L to the df, that is L to the df over 2. And so now if you assume that these clusters with that magnetic moments rigidly respond to an external field, you get a modified prediction for the susceptibility, which looks like this. L to the capital L, that's the size of the sample, divided by small l to the d, again, the number of blobs. L to the df over 2, the contribution of each blob, and this scaling function of the magnetic energy divided by temperature. So now if you do a little bit of expansion, so Z being the field divided by kT and small m magnetization per spin, what you find is that the first term, the linear contribution, is actually proportional to L to the df minus d. But you see that in general, if df is smaller or equal to d, this is not a singular contribution. Of course, there's the non-singular part, which will always be finite. So you have that cannot go to 0. There's a single spin contribution, if you want, that is going to remain finite. But then, if you go to higher orders, you find that there are potentially divergent terms. For example, the third order susceptibility is proportional to L to the 2 df minus d, and the fifth order susceptibility to the L to the 3 df minus d. And so if the fractal dimension is greater than d over 2, you see that this term diverges, and this term diverges even more, and so on. And so interestingly, whereas the linear susceptibility couples to a featureless spin-spin correlation because of the randomness of signs, and hence leads to a finite susceptibility at Tg. That's what I just said here. You see that chi3 couples to the square of that correlation function, and hence may pick up this divergence of the correlation length. And so this is well known, but what's remarkable is that it has been measured in the 80s, is that chi3 is a direct signature of the onset of this strange notion, which is this long-range amorphous order in spin glasses. And I'm showing you here the experiments of Laurent Lévy in 1988, and you see that if you measure the static susceptibility, third order susceptibility, chi3, it really goes up very high. There's a factor 100 between this point and this point. And so it's pretty convincing that something is critical here. Okay, so is something similar happening in real glasses? Well, there again, the story has been told this morning by Jorge. We know that real spin glasses undergo a second order phase transition, which is continuous, and it's in agreement with simple models with two spin couplings. But we also know from Derrida 1980 and Volines, Kirkpatrick, Tirumala a little later, is that there's another type of phenomenology which goes on the name of one-step RSB, or random first-order transitions, where, for example, multi-spin Hamiltonian can lead to phenomenology that's different from the spin glass case. And this phenomenology, again, has been recalled earlier, above some well-defined temperature in mean field that I'm going to call here T star. There are no local barriers, so the system is free to flow like a liquid. Then between T star and TK, there's some kind of local rigidity that sets in, so states can become metastable. And in finite dimension, you expect that if you expand on the mean field picture, and that was the contribution of Volines, Kirkpatrick, and Tirumala, the picture that emerges is that there are still many locally stable configuration in that temperature range, and so you should think of the glass as a kind of mosaic state of little glassites. So glassite is like the equivalent of chrysolite for this problem. It's small chunks of glasses, of frozen glasses, that have a certain size that's limited by the configurational entropy, because if there are so many states, these little glassites are quick to melt in a way and move to another configuration. So intuitively, that's why there's this inverse relation between the size of the glassites and the configurational entropy. And so what happens is that, again, the important thing is that there's a high frequency shear modulus that has appeared in this phase. The system is still liquid, but very slow, and there's local rigidity at the scale of L. And then below TK, that's up to now not reachable experimentally, then one believes that this configurational entropy will go to 0 and will reach this kind of ideal state of amorphous long-range order with an L that diverges. So let me give you a very simple argument for this sudden appearance of rigidity, at least local rigidity in the system. And this argument can actually be made very precise, and there's a paper by Ajime and Marc on that. But hand-wavingly, the way rigidity happens in the system is, recall this formula giving the shear modulus in terms of this affine contribution B, the Born term, and the contribution from fluctuations. Then in a kind of self-consistent way, you can think that the fluctuations are going to be small if the local rigidity is higher, because particles can't move around. So if you assume that sigma square is itself given by a certain constant times temperature divided by G, then you see that this becomes a self-consistent equation for G, and its solution is very easy to find. And what's interesting is that there's indeed a temperature T star, which is here equal to B squared over 4A, where suddenly a non-zero G pops up. And furthermore, there's a square root singularity when this shear modulus occurs. I mean, non-zero occurs. And if you look at experiment, this is actually, T star is traditionally associated with a mode coupling transition, and all these statements can be obtained within MCT or using replicas. And they lead these more elaborate calculations to the same square root singularities that, although in real systems this transition does not really exist, there's a kind of hint that something like that happens close to this MCT transition. And below the T star, as I told you, there's rigidity, so you expect barriers to exist. And this is a plot by Kivelsen and Tarjuk giving the energy barriers, the one that enters the formula for the relaxation time of the system, that seems to be constant above this T star temperature. And then when you lower below the appearance of local rigidity, then the barrier seems to grow when you lower temperature. Okay, so that's a quick reminder of all the phenomenology of glasses and the theory that has been proposed, at least the RFOT theory. But what I want to show you is how experimentally one can try to test at least part of this picture using the same tool as the one that's been used for spin glasses, that is nonlinear susceptibilities. So first remark, because glasses, we know, are in fact liquids on very long time scales, we expect that nothing singular can be present at zero frequency. So the static nonlinear susceptibility cannot be singular. We have to look elsewhere to find something interesting. And where to look is actually in the frequency regime where omega tau, the frequency times the relaxation time of the system, is of order 1. Because on these frequency scales, there's no difference between a completely frozen system and one that flows, because the flow would take place on much larger time scales. So one expects from very general arguments, and that's a prediction that we proposed with Giulio in 2005, that the existence of these quasi-frozen random clusters of particles in glasses should lead to a singular contribution for chi3, the third order nonlinear susceptibility, or chi5, or any of them actually. So chi3, I recall, is given by L to the 2df minus d times the scaling function g3 of omega tau, and chi5 to another power of L to the 3df minus d times another scaling function. And what we expect is that these functions gk must be hump-shaped in the sense that when omega tau goes to 0, there cannot be any singularity, any singular behavior of these nonlinear susceptibilities. So we expect gk to be of order 1 when omega tau is of order 1, and then dive back to 0 at lower frequencies. So this was what we proposed in 2005, and we managed to convince the group in Saclay, led by François Ladieu and at the time Denis L'Hôte, to start checking this. And unfortunately, it took them much longer than what we initially thought. So that's a little embarrassing for theorists who say, "Oh, it's going to be easy. You just have to look at harmonics, and it's going to work like that." And it didn't, and it took them years and years to actually manage to measure something precisely. But anyway, they did. And they were joined later by another group in Germany, in Augsburg, led by Lukenheimer. And I'm going to show a few of their results. So again, I recall these are the predictions, and this is typically what you find. So this is, for example, on glycerol at a temperature below T star. So we are pretty far from the MCT regime, but still at temperature such that the relaxation time or the relaxation frequency is not too small. And so what you see indeed is that, for example, look at k equal 1. This is the linear susceptibility. Nothing at all is going on. There's no hump. But then as you go to higher order susceptibilities, you see a clear hump. And chi5 is even more marked. What is interesting, and I'm going to mention that at the end, is that there's also something interesting in tails here. There's not only a hump. There seems to be a very nice power law regime at high frequency for these nonlinear susceptibilities. And so the prediction is that if there is amorphous order growing, the L to some power here, which governs the height of these peaks, should grow as you lower temperature, and that's typically what you see for glycerol again. That's chi5, that's the peak, and as you lower temperature, you see that the height of the peak increases. There are two sets of data, one coming from the Saclay group and one from the Augsburg group, and so it's pretty remarkable that they find very similar results, because again, the experiments are extremely difficult. So you see that there is indeed an increasing prefactor that means an increasing height of the hump as the temperature is lowered. So, for example, if you believe these predictions, then there should be, for the height of the peak, a relation between chi5 and chi3 at the peak, which is given by this exponent, 3df minus d over 2df minus d. And in particular is that if the fractal dimension of these frozen clusters is equal to the dimension of space, which is the prediction of this random first order theory, then you expect this exponent to be 2. And that's roughly what you find. I mean, this is the height of the peak of chi3 to the power 2, black points, and the height of the peak of chi5 in red points. This is actually on propylene carbonate, but it's also all the same result on glycerol. But having this nice increase of a correlation length, of an amorphous length, is satisfying, but not completely, doesn't solve completely the problem, because actually the increase of the volume of particles involved in this collective rearrangements in glasses is only a factor 2 when temperature changes by 7% here. So factor 2 is not bad, but it's not the factor 100 that I talked about in spin glasses. And as you, of course, imagine, it's nearly impossible to go to much lower temperature anyway. Something else that they've done is to look at what happens in the aging regime. So now you lower the temperature to a regime where you're going to be able to observe the system out of equilibrium for a while and then reaching equilibrium after a long time. And the prediction here is that for a certain age of the system TA, you expect this chi3 to increase as this amorphous length that's now going to grow with age to the power 2df minus d. And you also expect, as in aging systems, the effective correlation time to be age dependent and to increase with the age of the system. That's what we've seen this morning, for example, in Victor's talk. And so this graph is maybe a little hard to read with the limited amount of time I have to explain, but essentially what you see here is the linear susceptibility. So the equilibrium curve is the black curve, and the points that you see are for a given frequency as a function of the age of the system. And if you rescale them as f over this time age-dependent relaxation frequency fa, or f over the equilibrium frequency f, what you find is that all the data points fall on the same curve, which means again that there's nothing that you can see in the linear contribution. The linear contribution would have a negative power here, so you expect the linear contribution not to age, and that's what you see here. I mean, there's of course a trivial contribution which comes from the shift of the relaxation frequency, but apart from that, all the points are on the equilibrium line. But you see that it's not true for the chi3 curve, and what you see is that systematically, for a given age of the system, the contribution is lower than what it should be in equilibrium. What it means is that this length scale here is lower at a finite age than what it should be in equilibrium. And so from these curves, you can extract the length scale as a function of the age of the system. The different color points correspond to different measurement frequencies, and one prediction of the theory is that all these points should define the same curve, which is this age-dependent length. And you see it works pretty well. There's a 10% increase of this age-dependent amorphous length as the age of the system goes from 1,000 seconds to 10 to the 5 or 10 to the 6. Something I don't have time to discuss is that these dependencies are compatible with energy barriers growing, like the size of these domains to a certain power psi, and an exponent that's not easy to pin down, but 1 would work or 1.5 would work. These are two special values that have been proposed in the literature. But the main message here is that you see something happening in aging glasses where clearly something correlates more with time, and that's our interpretation is this amorphous order that grows. Okay, at this point I'd like to mention another nonlinear susceptibility that has been proposed in the literature a few years before, just to try to clarify the relation between the chi3 that I talked about, which is a very intuitive definition of nonlinear susceptibility, is the H³ contribution to magnetization, or H5 contribution to magnetization. The other family of nonlinear susceptibilities are called nonlinear for a slightly different reason. So, as I said before, chi3, where the chi3, chi5 were studied, another nonlinear susceptibility called chi4 was introduced by, in particular, Giorgio and Silvio and collaborators. And it was introduced as a tool, again, to reveal spatially correlated dynamics. And so the idea is the following. If you look at a spatial correlation function G4, which is how the system evolves, delta rho is the difference between the density around site X and the equilibrium density. So delta rho can be positive, for example. There's an excess density at site X at time 0, and it relaxes over time. So you look at this 2-point correlation function. But then you look at how the temporal evolution of the system is correlated in space by looking at the same object at a point at a distance r in space. And then you subtract the 2-point correlation squared. So this is a reasonable definition for looking at how the dynamics of the system is correlated in space. It's the spatial correlation of temporal correlations. And if you integrate this correlation function over all space, then you can define a kind of susceptibility. So you see, this is the analog of what would define the nonlinear susceptibility in spin glasses, and that's why this was called a nonlinear susceptibility in this case too. And if you look at simulations, for example, there's simulations from Ludovic Berthier, you see that as the temperature goes down, the peak of this chi4 increases, showing that the system becomes more and more correlated as the temperature is decreased. So what's the relation between this chi4 and the chi3 that I talked about? Well, in our paper in 2005 with Giulio, we argued that in general, so these are really, very hand-waving way of stating the result, but in inverted commas, chi4 is larger or equal than chi3, which means that chi4 can diverge even if chi3 does not. And that's important because in some model systems, like kinetically constrained models, where there's glassy dynamics in the sense of the dynamics getting slower and slower as you reduce temperature in a non-Arrhenius way, there's correlated dynamics, but no amorphous order. And in this case, you expect chi4 to diverge, but chi3 to remain trivial. And so, in a way, chi4 is not able to grasp this thermodynamic nature of the ordering that chi3 is able to measure. There are other problems with chi4. For example, we wrote a long paper with many authors, first of them being Ludovic, to discuss the fact that on top of the fact that chi4 does not really catch what we want, it's also ensemble dependent. You expect chi4 not to be the same for an NVT ensemble or an NVE ensemble, which models a little bit its interpretation. Okay, for those of you who are interested, you can look at the papers. By the way, so I suddenly remembered that Giorgio was also one of the first to think about these things. And so there's a paper by Giorgio in 1999 where he measures using chi4-like observables how this length scale characterizing the correlation of the dynamics increases with the age of the system. And so he finds using two ways of extracting this length scale that indeed grows. But again, this is, well, similar, but not exactly the same as the one that you extract from Chi3. Okay, so I'm nearly over. So as I said, there are, at least at the end of the spectrum in each cases, two opposite viewpoints. One is that the local slowing down of dynamics is what's going on in glasses. It has nothing to do with anything thermodynamic happening. For example, kinetically constrained models, that's been discussed a little bit by Mathieu, where you introduce by hand kinetic constraints that slow down the system, means that the system is going to slow down. And in this case, the idea that boundary conditions propagate and fix what's in the middle of the system is not correct, at least not in a thermodynamical sense. And as I've mentioned, in these very simple models of glasses, there's nothing going on in these nonlinear susceptibilities. So you don't expect to see the peak of Chi3 and Chi5 growing, or to see an age-dependent amorphous length in these models, whereas experiments have suggested that. On the other hand, this incipient amorphous long-range order is predicted by random first-order theory, and I have the weakness to believe that RFOT accounts for a lot of the glass phenomenology, but of course, it's still debated. Boundary conditions propagate over this point to set length scale that's been already mentioned, where you freeze the outside of a cavity. What happens to the inside? Is it still free to flow, or is it pinned by the boundary conditions? And from numerical experiments, first done by Andrea and collaborators, you see the increase of this point to set in numerical experiments. Also in some experiments now. By the way, the point to sets, I think that we were the first to suggest this protocol with Giulio, but the name point to set and going much further in the understanding was proposed by Andrea and Guillaume. So as I said, I think that the idea that the glass is a kind of mosaic of cooperatively ranging regions with size L point to set is pretty convincing. And this idea of CRR, cooperatively rearranging regions, that's been proposed as early as 65, can start to be checked experimentally using this idea of nonlinear susceptibilities. Of course, there are many open issues. Some of them have been already mentioned. RFOT is anyway only constitutive in mean field, or now for hard spheres in infinite dimension. But of course, it's really hand waving in finite dimension. We can't hide that under the carpet. And this T star that I talked about, where the system is supposed to acquire a local rigidity that makes the whole construction consistent. Again, you cannot speak about metastability unless you have some local rigidity that prevents the system to just continue flowing. Then we know, unfortunately, that this is not at all a sharp transition in real systems, but at best a soft crossover. So this has been emphasized by Mathieu earlier. Even in the absence of stronger critiques, there's no, we would need more quantitative results to check whether this picture is correct or if it's just a fuzzy scenario. It would already be great if the fuzzy scenario is correct, but we clearly need more to ascertain that it's the case. And as you've heard a little before, there are challenges even to this fuzzy scenario that are brought about by the swap acceleration simulations that Mathieu talked about. As I mentioned, Chi3 increases. That's in a way exciting, and that's what we hoped when we proposed that with Giulio. But the increase is only a factor 2, a factor 4 for Chi5. It's good, but it's not really spectacular. Again, the spin glass factor is 100. So this may be the fate of the glass problem, but it's a little frustrating. And so that's why I would like to come back to something that looks very clear in the experiments, and to my knowledge has not been explained quantitatively, and that there might be some room for theoretical predictions to maybe bolster the whole picture, is that there seems to be a pretty wide region in frequency where there is a parallel behavior of chi3 and chi5. And I think this tells us something, but I'm not exactly sure what it tells us. I think it tells us something about the dynamics that's going on length scale that are shorter than the point to set length, that in a way are collective as well, and that we are able to catch at higher frequency, but I'm not totally convinced that this is the case, nor how to make a quantitative theory of that. Okay, maybe there are other ways to test the theory, like nonlinear elasticity or nonlinear flow curves that one can think about. I have no time to expand on that. But going back to spin glasses, what's strange is that although, as I've shown, the chi3 divergence was taken in the 80s as a proof of the existence of a true phase transition in spin glasses towards this crazy notion of long-range amorphous order, this has not been studied experimentally, this chi3, below the spin glass transition. There's no chi3 experiment, AC chi3 experiment in the aging regime, where we'd like to see, for example, if experimentally one sees as well a growth of this length scale as a function of the age of the sample. And I'm really surprised this has not been done yet. And I've tried to convince experimentalists in Saclay, but it didn't really work out. For example, you know that in spin glasses there's this very spectacular effect of temperature cycling, where you lower the temperature, the system ages again, and when you go back to the first temperature, you find that the system actually has not aged. So there's this rejuvenation and memory experiments. I think it would be really interesting to couple these experiments with chi3 measurements that would allow us to understand what's going on in terms of length scales to explain such a bizarre memory effect. And there's also an interesting prediction of what chi3 should look like around the Almeida-Thouless line if it exists. And so that again could be experimentally interesting to look at. So at this point, I just want to end and thank you for your attention.
Thank you, Jean-Philippe. Thank you very much. Question, Jorge?
So what happens to chi3 and chi5 in the mode coupling transition in a really mean field model?
Yeah, it diverges.
They diverge.
So that's something that we did with Giulio and Marco.
Okay.
In a way, in a way, it's just a precursor of what's going on. I mean, it's different, but it's a precursor of what's going to come.
Can you say a few more words how nonlinear elasticity can be a promising test? Because we know a lot about nonlinear elasticity. So, what do you have in mind?
Well, okay. We have thought more about the nonlinear flow curves, but I think that by thinking more, and I think Giulio has thought about these things, so there's a paper by Giulio and Pier Francesco on these nonlinear elasticity that you expect in general. So I think that it would be interesting to think more about it in these lines, but I don't have a specific...
yeah, I mean, we know that all the high order moduli don't exist. They actually diverge. Not the shear modulus, which always exists, but the high order are always either marginal for the second.
Right, so you see, if you could relate this to the measurements of chi3 and make some link between the two to see whether, I mean, it's very vague at this point, it's just open issue.
Yeah, okay, thank you, it's very interesting, thank you.
Giorgio?
I have one question. I remember a paper by, I think, Walter Kobb, in which they were measuring the dynamic correlation lengths in glasses, and they were seeing, as usual, that was increasing when decreasing the temperature, but at a certain point it was saturating and maybe changing behavior.
Yes.
I think, I mean, I was very confused by that paper. My feeling was that was something wrong, maybe, but I would like to know your comment.
No, okay, so that was at a point where, you know, it's true that there's something that is not well understood, which is how do you, well, a little bit related to Jorge's question, how do you cross over from the MCT regime to where this length scale is supposed to diverge to the point to set length scale? Or is it what one measures? And so a naive idea would be that actually the length scale that you measure grows because of MCT and then goes back because the point to set length is still small. But first of all, this might not be the case. You could imagine a scenario where actually the point to set length is already large at the MCT transition, which is depleted because of fluctuations or finite dimensional effects or whatever. And so at the time, I think that people really wanted to see whether there would be a non-monotonous behavior. So I don't know what's the follow-up. Do you know, Giulio, if this paper is still considered valid or?
I think it's, well, they do that when they change liquid, they don't see really the cloud anymore. So it's not clear how much is the but it's true that it's still an open question.
Are there other questions? If not, I think we can thank all the speakers of today. We can close the day. We have plenty of time to go home to decide how to dress tonight, right? Please remind